Hello, grade 9s. Today we're going to talk about the power to a power exponent law. That's where I take a power that already exists. It's included inside my brackets, and it's raised to another exponent. Okay? Now, when we did our activity the other day, we kind of saw it or started off at this base level where I had a single power that was raised to an exponent. Now, just as a little reminder, when we're talking about an exponent always applies to what's immediately next to it. So in this case here, this outer exponent n applies to the whole bracket, which means to every single thing inside. And that's true for every single one of these examples here because the exponent n is right immediately next to that bracket. Now, the little shortcut that we identified or we noticed yesterday is that when we have a power and we're raising it to another exponent, we can multiply those exponents to get the new exponent that will apply to the same original base. So, let me just get my color back here with this one. Here, my original base is x. So x will remain my base, and I'm multiplying the exponents, m times n. So m times n. Now this was stage 1, when we had a single power inside. But we also noticed that this would also be true when I'm talking about a collection of powers multiplied together that is being raised to an exponent. Now, this is only true if there's multiplication on the inside of that bracket, right? X to the power of m and y to the power of m are being multiplied together, or there's division going on. It does not work for addition and it does not work for subtraction within my brackets, but it does work for multiplication and division. Now, just like before, we said we were going to multiply those exponents together. That's true. X is the original base. M is the original exponent. The new exponent is going to be m times n. And I'm going to do the same thing. We're going to repeat it. Y is the original base. M is the original exponent. And we're going to times it to get a new exponent of m times n. Now that's true if I have multiplication, but it's also true if I have division. So same story, x is that original base, m is that original exponent, and we're going to times it to give me a new exponent of m times n. Do the same thing with that denominator. Now something to kind of keep in mind is we're not moving anything around. We are simply applying a new exponent to the original base. So this power was originally in the denominator of my fraction. This new power with its new exponent is going to remain in that denominator of that fraction. This one was in the numerator. It's going to remain in the numerator. You're not shifting the position of anything. We are simply applying a new exponent to the original base. Okay. Now, we can figure this out or see this a little bit more clearly when we write things out as repeated multiplication, but there is a couple of things that are really important that I want to just jot down here. First of all, this rule does not apply if there is addition or subtraction inside the brackets. So if I had something like x to the power of 2 plus y to the power of 3, all in brackets to the power of 5, this law does not work. It does not work for addition. It does not work for subtraction. The only time it works is in multiplication, division, or just being a single power on its own. This is a really important piece of information to kind of to grasp onto. And it's probably a really big common mistake that we see not only in grade 9, but continuing in grade 10. So if you can nail that down now, you are going to be super ahead and prepared for next year. Okay, when we are distributing that outer exponent to the inside of my brackets, it's really important to kind of consider what happens when there's a negative involved. So we're going to take a look. We're going to write down kind of a rule here. The exponent outside the brackets also applies to negatives. We can treat the negative as a -1 and evaluate that power. Okay, so exponent outside the brackets also applies to negatives. It is not just applying to variables or to numbers, but also a negative if a negative exists inside my bracket. Now, if that negative is attached to a number, oftentimes we just auto deal with it. But if that negative is just sitting as a coefficient in front of a variable, sometimes we forget about it. So I want to put this out in the open now that we all know what we're talking about. And I'm going to make up an example, and that example is, what if I had negative x, y, all to the power of 2? How would we apply this law to what we're about to do? Now I'm going to do this in 2 ways. Way number 1 is that I'm going to write this out as repeated multiplication and simplify it. Way number 2 is I'm going to use the shortcut of the exponent law to show you that we'd get the same thing. So way number 1 means repeated multiplication. Since this exponent of 2 is immediately next to the bracket, it applies to the whole entire bracket. So that negative xy in brackets is repeating twice. When I do this, I have 2 negatives multiplying together. A negative times a negative will result in a positive. I have x times x, which can simplify to x squared. And I have y times y, which will also simplify to y squared. Now notice that in this case, the negative went away because a negative times a negative, an even number of negatives multiplying together, will end up with a positive. Now if I were taking a look at this and wanted to apply that exponent law instead of writing it as repeated multiplication, one of the ways that I can think about this is to rewrite what's inside of the brackets, but actually include a -1 instead of just a negative x. Because I know that any variable has a coefficient, whether that coefficient is visible like a 2 or a 7 or a 15, or it's hidden like a 1 or a -1. I know it's always there. And when I write it out this way, or I at least think about it this way, I can very easily see every single thing that outer exponent has to apply to. I know it has to apply to the -1, which currently has an exponent of 1, the x, which currently has an exponent of 1, and the y, which currently has an exponent of 1. And when I do that, I'm going to apply it to every single thing inside that brackets, and I'm multiplying those exponents together. In this example, the -1, the x, and the y all have an exponent of 1, so 2 times 1 will give me 2's. Okay, now what I mean is that when we apply this, when we have an exponent on the outside, we apply it to the negative, we can treat that negative as a -1. That's what I mean here. And when we simplify this fully, I could actually evaluate that power. So I know that -1 squared is going to be a +1. So I could think of that as 1x squared y squared. But I do know in the simplified version, I don't include 1 there because that 1 is redundant, right? I'm saying 1 times x squared, and I know that 1 times x squared is just x squared. So there's no need to write the 1. Now this is a little bit long-winded. I am not expecting you to show me that -1 being squared. But it's a really good way to think about it and practice with it before it becomes second nature as you go through the examples. Speaking of examples, we have 6 of them and then we are done. I'm going to do a couple of these as repeated multiplication. Probably not all of them, but just to kind of show us what we've got. So I'll do the first one as repeated multiplication, just because I don't know if we all got a chance to talk about the fractions at the end of the activity yesterday. So here I have 4/7 all to the power of 2. Now that 2 is immediately next to a set of brackets, which means everything in brackets gets included in the repeated multiplication. So I get 4/7 times 4/7. Now, if you remember from last unit, when we multiply fractions, we go top times top, bottom times bottom, right? So I have 4 times 4, which could be simplified as a power. I could write that as 4 squared. And bottom times bottom, 7 times 7, which could be simplified to be 7 squared. Now I'm asked to simplify, not evaluate, so I do not have to tell you what 4 squared and 7 squared are. This is, in fact, my final answer. Now, of course, you can jump straight from the beginning to the end. I just wanted to talk about that repeated multiplication in this first example. In the second example, though, we will just straight up jump. That 10 exponent on the outside of my brackets will apply to everything inside my brackets, which means it'll apply to the top and to the bottom. And of course, I will multiply those exponents together. And when I do that, we get x to the power of 90 over y to the power of 20. So again, we just hop straight to that final simplified answer. No problem. We could have shown repeated multiplication, but we do not have to. Okay. Let's talk about the next one here. The next one does, in fact, have a negative involved, and I'm going to treat that negative as if it was just a -1 out in front. So I'm going to rewrite this. I'm going to put -1, and I'm going to times that by 2 times a squared times by b cubed, all to the power of 4. Oops. Times a squared. There we go. I like to write it out with that -1 out in front because if we always think about it in this way, it could help us get to that simplified final answer in both simple examples or complex examples. Okay? When I look at all of my values I'm multiplying together inside my brackets, some of them have secret exponents. I'm going to write them in so that they're all visible to us. So when I distribute that outer exponent of 4 to every single power inside my bracket, I know what I'm multiplying with. So here I have -1 to the power of 1 times 4, which is 4. I have 2 to the power of 1 times 4, which is 4. A to the power of 2 times 4, which is 8. And b to the power of 3 times 4, which is 12. Now, to simplify this fully, I've always expected to evaluate that -1 power. I know -1 to the power of 4 because 1 to the power of anything will be 1. But when I'm talking about negative, an even exponent will end up with a positive result. An odd exponent will end up with a negative result. So since I have an exponent of 4, I'm expecting this to end up being a positive. So my final answer looks like 2 to the power of 4, a to the power of 8, b to the power of 12. Okay, jumping to the next one. When I take a look at the next one, I have 100,000. Now I look at that number and I think, hey, I can write that as a power with a smaller base, right? I don't have to leave that as 100,000 to the power of 1. I can rewrite that. What could I rewrite it to? Or as? Hopefully one of you yelled it even though I'm not there. You could actually rewrite it as 10 to the power of, I count the zeros, 1, 2, 3, 4, 5, 10 to the power of 5. So I'm going to just rewrite this. I'm going to add that secret exponent of 1 on the y, just so I can clearly see it. And then I'm going to go ahead and distribute that outer exponent to 4, multiplying it in with all of the current exponents. Gives me 10 to the power of 20, x to the power of 16, and y to the power of 4. Okay, we got 2 more, and then we are done. So let's tackle it. Just like before, I see I have a negative here. I'm going to rewrite this with that negative being a -1. Just so I can see it, I'm writing any hidden exponents there to be visible, so it's really clear to me what I'm multiplying by. Okay, oops, sorry, that flipped as I coughed. Okay, as I do this, I'm going to go ahead and straight up distribute. I have -1 to the power of 5. I have 7 to the power of 15. I have x to the power, hold on. I don't have 7 to the power of 15. Hopefully you all gasped in horror. I have 7 to the power of 10. 2 times 5 is 10. Good, I knew that. Then I have x to the power of 15 and y to the power of 10. Now, of course, I'm always evaluating my -1 power. Always, 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 because it's not a simplified form. Now, again, that exponent is odd, so I'm expecting a negative result. So I'm just going to represent that as a negative in front of the rest of my value. The really good thing about treating this negative separately from that 7 is eventually when we start combining exponent laws, it allows me to then use a power with a base of 7 maybe in the denominator, maybe later on that I'm multiplying with my numerator, and not think, oh, these two things are different because there's a negative attached to it. It allows me to kind of separate them so I can do some further simplification. So the more I can separate that negative out, the more I can potentially do in more complex questions. Okay. Last one. Speaking of complex questions, looky what we have here. Okay, so this one is not only a power to a power, but I also automatically, when I'm looking inside my brackets here, when I'm looking at my fraction, I see something at the top that can be simplified with something at the bottom, right? I see two powers that have the same base. 3 to the power of 7 and 3 to the power of 2. Now, technically, when we go ahead and we do this work, it's typically easiest to continue to follow BEDMAS, which means I would like to simplify my brackets before I apply that outer exponent inside of it, which means I want to simplify what's going on there. And what's going on there is 3 to the power 7 divided by 3 to the power 2. We learned and we know that we do what with the exponents? Hopefully you all yelled, subtract. You'd all be correct. Way to go. Now that negative is just chilling there. It was chilling there before. It's going to stay there after. No sweat. But I get 7 minus 2, which is 5. Now the a to the 13 was hanging out in the numerator. I didn't touch it. I didn't do anything with it. So it stays exactly where it was. Same with the b to the power of 4 and the c cubed, as well as that 3 exponent outside that brackets. Okay. As we go on here, I am going to just rewrite the negative and the 3 to the power of 5 to be a negative 1 and a 3 to the power of 5. And actually, I'm not really going to rewrite it as much as I'm just going to separate it a little bit at the top here. I'm going to backtrack. There we go. Just so that we can do both of those steps at once. A step doesn't have to be a visible step. But that way, when I'm applying this exponent on the outside to everything in the brackets, I don't miss anything. Okay? So I'm going to do that. I have negative 1 to the power of 3, because 1 times 3 is 3. I have 3 to the power of 5 times 3 is 15. A to the power of 13 times 3, which is 39. B to the power of 12. And C to the power of 9. Now, of course, I am not leaving my negative 1 cubed as is. I'm going to evaluate it. I know I have an odd exponent, which will end up with a negative result. So I'm just going to write negative 3 to the 15, a to the 39, over b to the power of 12, c to the power of 9. Okay. Those are all the things. Those are all of our examples. A couple of things to keep in mind. Obviously, there's practice. We all knew that. Not a surprise here. But there's also a quiz coming up. We did talk about this. The quiz is already planned. Please take a look at Teams to confirm that date. But it is happening pretty soon, next week. Okay? Otherwise, that's it. That's all. Have a great day, and we'll see you after the weekend.